In this video, we're going to discuss about DC machine construction, the various parts in a DC machine, including the stator, the rotor, the yoke, the poles, the field windings, the armature conductors, the brushes, and of course, the frame, which is the outer part of the machine. So going back to our diagram in figure 1.7, we can see different parts of a DC machine, including the stator, which is the stationary part, as we had looked earlier on in our video clip. The stator, which is the stationary part, which is normally the outer part of the DC machine. And then in the stator, we have the steering, which is the yoke to which it is attached. The steering is the yoke. Yeah, we can see the yoke here. We can see the yoke, which is the steering. We can see the yoke. And then number 2, we have magnetic poles, around which are in the magnetic poles, we have field windings. In the magnetic poles, we have field windings. These are the poles. Yeah, you can see this is a pole, and here we have a pole. In these magnetic poles, we have field windings. Yeah, we can see field windings. Now this is another field winding, that part. We have a field winding. Then in the field windings, these are many turns of a conductor wound around the pole core. On the pole core, current passing through this conductor creates an electromagnetic field. This is just the structure of a DC machine. The structure of a DC machine. We have the teeth. These are the teeth on the armature. These are the armature conductors, the black ones. In the teeth are the armature conductors. Then we have field windings. Then we have the brush. Then we have this is the laminated core. This is the laminated core. Yeah, this is the laminated core. And then we have brushes. We have the laminated armature. We have the pole tip. Then we have the poles. Then we have the commutator. Inside the commutator, we have segments. And then we have the yoke. Then we have the base. This is the base. Then you have seen that. From that, we have the base. Then moving on to our next point. We have a rotating part, which is called the armature. The armature are mounted in bearings. We have the armature here from our drawing. We have the armature. We have the teeth of the armature and the armature conductors. So the laminated cylinder, we have seen the laminated core. The laminated cylinder of iron or steel is called the core, on which the teeth are cut to house the armature windings. That is the single all-matrix conductor system, and the commutator, which has segments, as we had seen. So the armature windings can be divided into groups. We have 2 groups. We have the wave windings and the lap windings. In wave windings, there are 2 parts in parallel, irrespective of the number of poles. Each part supplying half the total current output, and wave wound generators produce a high voltage but low current outputs. They produce high voltage but low current outputs. In lap windings, there are many parts as compared to wave windings, where we have 2 parts in parallel, as the machine has poles. So the total current output divides equally between them. Lap wound generators produce a high current and low voltage. To compare between the two, between the wave windings and the lap windings, the wave windings has 2 parts, while the lap windings has many parts. Another difference is that the wave wound generators produce a high voltage, while the lap wound generators produce a low voltage output. In wave windings, we have low current outputs, but in lap windings, we have a high current. So looking into our next thing, we have the shunt, series, and compound windings. Those are the type of windings found in DC machines. We have the shunt wound machine. We have the shunt wound machine and the series wound machine. The shunt wound is the same as the shunt wound. The shunt wound. The shunt wound is the same as parallel. Is the same as parallel wound. Is the same as parallel wound machine. This is the same as parallel wound machine. We have the parallel and the series wound machine. So in shunt or in parallel wound machine, the field winding is connected in parallel with the armature. You can see here the field winding connected in parallel with the armature. While in the series winding, the field winding is connected in series with the armature as seen in figure 1.8b. So the machine is said to be series wound. Series means the field winding is connected in series with the armature, while in parallel or in shunt, the field winding is connected in parallel with the armature. So a compound wound machine has a combination of both the series and the shunt windings. So an armature reaction, we define armature reaction. Armature reaction is the effect that the magnetic field produced by the armature current has on the effect of magnetic field produced by the field system. That is the definition of armature reaction. The armature reaction effect, you can reduce it by fitting compensating windings. In generators, the armature reaction results in reduced output voltage, and in a motor, the armature reaction results in increase in speed. So moving on to our next point, we have seen that in generators, the armature reaction results in reduced output voltage, and in a motor, the armature reaction results in increased speed. So to find the EMF generated in the armature windings, to find the EMF, that is the electromagnetic force generated, the EMF the EMF is the electromagnetic force. The electromagnetic force is the EMF in armature windings. So you let Z, you consider you let Z to be the number of armature conductors, then phi to represent the flux per pole in Webers. Webers is the SI unit of flux. And then P is the number of pairs of poles. And N is the speed. N is the armature speed in revolutions per second. So to find the EMF generated by the armature, the EMF generated by the armature is equal to the EMF generated by one of the parallel paths. So each conductor passes 2p poles, that is the number of poles, 2p poles per revolution, and thus it cuts 2p flux, that is the flux there, 5 flux Webers of magnetic flux per revolution. So hence flux cut by one conductor per second, the flux cut per is that 2p phi n. 2p representing the number of two parallel paths in wave winding, that is the number of parallel paths in wave wound. Then this is the flux phi, and n is the speed, SI unit being Webers. And so the average EMF E generated by conductor is given by E, that is the EMF is equals to 2 times the number of poles times flux multiplied by N, this is the number of speed in volts. Since 1 volt is equals to 1 Weber per second. So you let C to be the number of parallel paths through the winding between positive and negative brushes. So we said in wave windings we have 2 parallel paths, while in lap windings we have a number of parallel paths. We have many paths. That's why we present P as the number of poles. But in wave windings, we only have 2 parallel paths. So moving on to our next point. The number of conductors in series in each path is equal to Z, Z being the number of armature conductors, and C being the number of parallel paths. Z being the number of armature conductors, and C being the number of parallel paths. So to find the total EMF between the brushes is equal to the average EMF per conductor. The average EMF per conductor. This is the average EMF, that is 2p pi n of Z divided by C being the number of parallel paths. So therefore the EMF between, so E is equals to 2 times P pi n Z divided by the number of parallel paths. Since Z, P, and C are constant for a given machine, then the EMF is proportional to flux multiplied by speed. However, 2 pi n, that is 2 pi n, 2 pi n, 2 pi n, 2 pi n is the angular velocity. 2 pi n is the angular velocity. 2 pi n, 2 pi n is angular velocity in radians per second, in radians per second, in radians per second. Hence, the EMF generated is proportional to flux and angular velocity. The generated EMF E is directly proportional to flux and angular velocity. So we have seen from our discussion today that the number of parts in a DC machine, including the stator, the number of parts in a DC machine, including the stator, which is the stationary part, the stator, which is the stationary part, the steering, which is the yoke, the magnetic poles, the field windings, the armature conductors, the brush, the nominated armature, the commutator, the pole tips, and the pole cone. And then we have a rotating part called the armature. It's mounted on the bearings, housed in the stator, and having a laminated cylinder off, which is called the core. And we have seen that we have wave windings. We have 2 armature windings can be divided into two groups, that is the lap windings and the wave windings. The wave windings having 2 parts in parallel, while the lap windings having many parts in parallel, as the machine has poles. So in wave windings also, they produce high voltage, that is the generators produce a high voltage and low current outputs. While in lap wound generators, they produce a high current with low voltage output. Then we have seen the shunt, series, and compound windings. The shunt wound machines have the field winding connected in parallel with the armature. The series wound machine having the field windings connected in series with the armature, while the compound wound machine has both series and shunt wound machines. To find the EMF generated in armature windings is to find the EMF generated is 2p phi n multiplied by Z divided by the number of conductors in the series path. That was all about our discussion today.